So my name is Devlin. I'm a principal researcher at Microsoft Research Cambridge, where I work on machine learning for non-player characters and agent control. I want to share today a few things that I've learned about just trying to get this stuff to work. A lot of deep reinforcement learning researchers particularly will come and talk to you about how they took an existing fixed game and they made their agent play it. I'm going to not do that. My aim today is to completely reverse the problem and say, assume you have an agent or a learning algorithm, how do you, and you're building a game, how do you make sure that that game is amenable to your agent so the agent likes to play your game, okay? For some context, I like to think of game-playing agents in terms of this like 5 levels of autonomy in game-playing AI. Right, so right down this end, we have open-loop controllers that are not responding in any way to the environment. They're just dumb, fixed, instruction-following things that just go in a straight line or just follow something completely fixed. I can barely think of any games that would actually use this. The only thing I can really think of is Lemmings, like they're not really reacting to much, just following that policy strap. So really, a lot of what we tend to do is more in this rule-based controller space, finite state machines, behavior trees, these types of methods. But as we start to progress more and more towards more autonomous agents in games, we can relax the assumptions about what we know about the environment. So right down here, we have to assume that we know perfectly before the game even begins exactly what the agent should do. Here, we're assuming that we can write down a set of rules for what they should do in a particular state, but we know that we need to actually query what state they're going to be in. When we get to here, we start to just assume we've got some knowledge, like maybe a forward model or preconditions and postconditions, and we can start to plan. But the place where I spend most of my time playing is down here, where we no longer can make that assumption, but we assume that we do have some assumed data. So particularly when we want to do things like modeling how humans play your game, or how you should respond to how humans playing your game. Alternatively, you can go one step further and we assume that there's no prior data. We don't know how the humans play the game. We don't know what we want to do in the game at all. So we're just going to have to interact with the game and learn how to do it. And on the very far side, we're going to just put an agent into a game that it's never seen before and it has no idea about the environment, the geometry, or any previous data or interaction with it. And it's just going to learn. I'm not going to spend much time down there today. I have done some things in this space around behavior trees and things in this space around like planning, particularly with MCTS in collaboration with an indie game studio called AI Factory. But today I'm going to talk about things more in the imitation learning space, where we have the driver task system in Forza Motorsport, and some reinforcement learning work that I've done, including the collaboration with Age of Empires 4. I'm not going to talk about this side. I'm really keen today, though, to meet the brave souls that are going all the way over here. In particular, you can talk to Diggle about this one on this side. But I'm going to talk to you about these two sorts of spaces. And that's not to devalue these. Like 90% of the game playing talks today have been more in this space, and rightfully so, because the majority of the time, these are the right tools for the types of problems. But I just wanted to show you, like, if you want to go this way, if you want to be a bit more autonomous, here's some things that might help. And it's not this discrete, right? Like, I try to think of it more of this like cat-dog continuum, right? Most of the times, and if you watch our GDC talk on Age of Empires, you'll see the rest of the system. Most of the time, it's a big hybrid system, and we're going to learn some components, but other things are going to be rule-based, some bits are going to be utility systems. There's a big mix of everything to create the agent. So personally, I'm more of a cat person. I like these wild cats down here. These things are good, obedient dogs, and they're really useful when they're the right thing to choose. But if you want to let them loose, then this is the space. The problem, though, is not that slide. Like, people get really excited. They see these results, particularly as a machine learning researcher, right? We come in and like, we solved Atari, man. We're going to solve your problems. We've got this. And then people come in and do really impressive things in games with huge teams and huge resources. But then when you actually try it out on your own, people often fall into this gap, right? This is a meme from 6 years back now. We've learned some things since then, and I hope we can share some of that to try and make sure that when you try this, that you don't fall into this trap. And in particular, I find that this problem is because we build up on a very solid foundation of basic linear algebra subroutines are written in Fortran in the 70s, and they're solid, they're perfect, they've been battle tested for years. And on top of that, we take billions of dollars of investment over the last 10 years in deep learning, and we start to get a piece that's roughly sort of useful and starting to be a stable part of the stack and things that I think can be utilized. But reinforcement learning is a little bit less shaky. And then you stick multiplayer games on top of this, and this is a very shaky stack. And it is, by the cats, gonna get destroyed. So all of my advice today is wherever you can, try and reduce your problem down to supervised learning. Right, get things back down to supervised learning. You can have a much more stable experience if all you're depending on is basic linear algebra and not that very top of the stack. So one example of that is in this example of learning to play. So we worked with World's Edge Game Studio on a collaboration on Age of Empires 4. As I said, there was a GDC talk in 2022. It's now freely available online to see the full system and the various choices we made. But the bit I particularly want to talk about today is doing reinforcement learning for controlling the ships here. So our RL agents are in red, and they're fighting the hardest in-game AI here. The video is a little choppy, but the RL agents win the vast majority of the time. The way we got towards that is, again, following these principles. So given time today, I'm not going to go over everything, but we use small symbolic states. We're not doing this from pixels. We discretize our action spaces. And in particular, I'm going to go through this multiple individual learners, weight sharing and weight freezing, and this is about how do we reduce it down to the simplest, closest to supervised learning problem as we can. So we want to control multiple ships, so we have some design decisions that we can make about how we parameterize this as a neural network. One choice is that we can do a joint action learner, and we just have one neural network control all of the agents. Right? This is like Alpha Star. It's going to take over your entire fleet of everything. But as you increase the number of agents that are under your control, if you're building bigger and bigger battles, you want to send lots of ships in, your joint action space is going to grow exponentially. And this is very expensive, both computationally to run, but also to learn. We need even more data if we do this. So alternatively, we can have multiple individual learners. And now, this is it's a simpler problem. I'm just learning from my state what action to take for my individual ship. And it's not going to grow in the number of parameters in the same way that this thing would. Now, given that we've reduced the number of parameters, we can make a trade-off. So we can either now do separate weights for every single agent, and every single agent is going to learn its own policy and act completely independently and to do this. Or we can share weights. And this doesn't mean that one agent is going to cheat and see what the other agents can see or share information in that way. It means that during training, they can share experiences. So now this one network is going to get 3 times the amount of data. And so each one is acting independently. It's only getting its own observations and taking its own actions. But we get 3 times more data through that, and we're only learning a single policy. So we're trying to train less parameters with more data, which is a win. It does mean they're all following the same policy, and we can do little things like condition on an ID or condition on some other factor to try and give them more sort of diversity in the behavior. But again, we can still do that. That's introducing a single additional input. It's far less additional parameters than going all the way to the separate weights. Now, given that we've got all that extra data, we still have a problem that we're training multiple individual learners at the same time. So these agents are acting in a non-stationary environment. The policies of the other agents are updating as they're acting, so their expectations over what should happen next is not matching what's happening because the other policies are updating, and this is a hard learning problem. This is like the top of the stack multi-agent learning difficulty. So the trade-off we made is to weight freeze. I'm really proud of this animation. Watch that chunk. I'm going to play it twice at least. Core concept is that we're only actually going to update one policy at a time. So we are throwing away some of that benefit of the extra data, but we are sharing, it's the same policy, so it's still getting, all agents are getting updated, but we're only updating one at a time so that there's no non-stationary problem. This agent is all the agents are acting in the environment, only this agent is currently learning, taking samples and updating its policy and changing its policy. That way, that one agent is acting in a single agent problem. The rest of the environment is static and following the same transitions as as if it was. So the only thing that is changing is that one agent. So here we throw away some of our data, essentially, right? What the other agents are doing, we're not monitoring that. So we are reducing some of our data, but it's a trade-off for stability, right? So we throw away some data, but we gain in stability, and gains in stability really help us reliably make sure that these agents train. However, that doesn't necessarily mean they're going to learn anything particularly interesting. So the next step, we were really thinking about, like, how do we make sure that they act in ways that other humans would perceive as human-like? So we ran a test. Very simple navigation task. Again, probably shouldn't have been a neural network, but that's what we do. These two characters are in exactly the same place in the same map, and they're going to be asked to run to the same location. One of them is a human player, one of them is an agent. I'm going to ask for a little bit of interaction here. So in a minute, I want to hear who thinks A and who thinks B is the most human-like, okay? All right, hands for A. Who thinks A is the human? And hands for B? I'm afraid the A's won. Okay, this could be a cherry-picked example. Okay, this could be one of the thing. And we might have chosen, if you're B, you might think we've chosen a particularly adversarial example here and made it nasty for you. And if you choose A, you might think that our agents are terrible. But as good scientists, we showed it to hundreds of people on the internet and asked them instead. And oh yeah, the agent, again, we discretize our action space. We build off the closest prior work, which was this nice paper from Ubisoft in 2020. We give nice dense reward signals. We use symbolic states, so we're reducing the amount of data that we need to use. We are using the privileged access to the game to make sure that we can reduce the amount of data that we need to train on. Nice dense reward signal, pack as much information as we can into that. There's some principles about how we design them that I can go into if we have time, but again, simplest possible instance of it, train the agents. We see that over time the agents learn. One of them was particularly high variance, but ultimately they learn policies that are approximately the same sort of time to distance as the humans. However, when we ask humans on the internet, what you'll see now is like some violin plots for different agents appearing. If the bulk of the dots are above the line, then people could tell that the agent was not the human. If the dots are below, then the agent has tricked the human. And the majority of people, most of the time, could get it right, that which one was the agent and which one was the human. Right? This reinforcement learning agent has not been trained to act human-like. It's been trained to run to the goal. Okay? And that's what it does, and it doesn't act like a human. However, because we did ask hundreds of people on the internet, we also asked them why they could tell the difference. And we just packed that information into the reward function, and then we get an agent that was completely confused people. So we see the bulk of the mass of the violin plot now is around dots. So you can do this sort of thing. If you get good at reward shaping, you can find good principal ways of adding additional information to your reward signal. If you've got that domain knowledge, again, this is where it's continuum, right? So I'm not assuming that I have no knowledge. I'm assuming I have some knowledge that I can like roughly structure into a reward function and quantify what's good and what's bad. But really, we want it to be more cap. We want to be more autonomous. And so one thing that we've been using a lot is a blending reinforcement learning and imitation learning. So if we assume that we do have some human data, right? We've done the human user study. We'd collected lots of data of people running to points. So we have those videos. If we can blend that with reinforcement learning, then we get a much more stable agent. And in particular, we got these results. I'll let the agent run. It just sort of slowly goes along. But in particular, this was really fun. And it made us ask like interesting design questions. So now the agent has confused the testers, the viewers. It's being judged more human-like than humans by the majority of humans. It made us really sort of question, like, what does passing this test even mean? Like, do you want the agent that like perfectly confuses human players and they don't know whether it's a human or an agent? Or do you want the agent that people can clearly tell a difference, right? They know there's something different about this video compared to that video, but they're wrongly attributing credit to the agent rather than the human. Like, which one do you want? It's a design question, though. I'm a machine learning person. I don't know. And so the study overall, we have, so like we built off the Ubisoft paper at the top that showed, you can do 3D navigation with deep reinforcement learning agents, and Ubisoft had some really nice follow-up papers as well about how you can use this for like really long distance navigation and things. I really recommend checking those out. We built on that to show that like high skill alone enough wasn't human-like, and there's a paper at ICML there. And then we had one at Chi, which was much more of a qualitative analysis of how people were assessing agents and humans and where the differences were. Our takeaway was that we could pass it with reinforcement learning and imitation learning. But actually, this was really a much more sort of macro-level observation and something that we've seen over and over again. Actually, the last time we had one of these conferences in Europe, I presented a very similar work around using MCTS with imitation learning. And essentially, it's those two objectives that pair really nicely: reward maximization and behavior cloning. And I really emphasize behavior cloning here. Like, keep it as simple as possible, right? For the machine learners in the room, friends don't let friends use Gale. Don't do it. Behavior cloning all the way. Keep it as simple as possible. This is just straight up supervised learning. And you know what? Supervised learning, behavior cloning does awful in sequential decision making if you leave it on its own. The only way behavior cloning works in theory is if you exhaustively cover the entire state action space and minimize your error, right? Which you're not going to do. We don't advocate for having exhaustive coverage of your state action space and training that. But if you pair it with reinforcement learning, when it gets out of distribution, and behavior cloning would often fail when it gets out of distribution, reinforcement learning can help smooth that point. It can break those moments of the behavior cloning agent being out of distribution and not knowing what to do. The RL policy will then give a stronger loss and stronger signal to learn how to correct itself and get into a good place. Similarly, reinforcement learning will, when it gets into a state and it goes, oh, all my options look the same, will often tend towards a random action, right? And this is often where we can tell that a reinforcement learning agent is not human-like. In particular, this showed in the MCTS work. We were doing a digital card game at the time, and the MCTS agent could often tell before the human players that it had won or lost the game. And so the MCTS agent at that point just starts throwing its cards around. Because everything's the same. What does it matter, right? Unfortunately, that was a collaborative card game. So the people that were paired with that agent were not really happy when they're still trying to play to win, and the other agent's like, right? It doesn't help. But blending with BC, then when everything looks the same as far as maximizing reward, then you choose the most human-like in your data set, right? And again, there's loads of other trade-offs that I find, like reinforcement learning is super sample inefficient. You need to do loads of samples. That's why we recommend symbolic state, simplifying a problem so that you minimize the amount of data that you need to train on, minimize those number of interactions. But if you have human data, you can bootstrap reinforcement learning. You get a good initial policy, so it's not randomly searching when you first initialize it. It's following something of a decent policy some of the time, and that gets you so much gain. Like the smallest amount of human data, it gets you so much gain as far as how much you can learn by reinforcement learning afterwards. So like, as much as you can, pair these two things together. Okay. Right, final stage. You've got your human-like agent and you've got your agents that can play. But really the thing that's been exciting me for a long time is how do we create agents that can collaborate with humans? And this again is part of why that motivation to being more CAD, right? If we put an agent, whether it's learn or a behavior tree or anything, if we put an agent into a game with a fixed policy, then the way that a human and that agent collaborate is the human learns how to collaborate with the agent, right? The agent stubbornly says, I'm going to do this. And the human has to figure out how to work around that, right? That's why we jump up and down and run around on the companion missions, right? And that's why we act in funny ways around it, because we know we're sooner or later going to get to the goal location. Our interactions aren't affecting it. But what if the agent was actually learning and adapting and interacting with us and accommodating for how we behave rather than us adapting to the agents in the game? This was really nicely shown, I think, by this team from Berkeley. So simplified game, this little overcooked clone. In particular, they show here this one. So they train some agents with self-play. Self-play is usually used in these settings. We train two agents together, and then they learn to play well together. But then you stick a human in there, and they don't play well together. You'll see in a minute when it loops over. The human's trying to go left, and the agent's like, nah, my friends go this way, my friends go this way. I've always trained with other agents, and they go this way. And so the human has to adapt and change. What they showed in this work was if you instead train an imitation learning agent and then train your reinforcement learning agent to learn an approximate best response to that, then you get more compatible policies with humans. They didn't go full cat, they didn't go to the learning side, like in adapting online, but they get a single fixed policy that is robust to other policies. And this is the big thing, right? Like the training teams of agents together, they learn how to play well together. Right? Machine learning overfits, reinforcement learning overfits. They learn how to interact well with each other. You can get a team of these agents to play well together. They don't necessarily play well with others. If you want them to play well with others, then you need to maintain a population of the behaviors that they might play well with. Okay? I forget why I actually added it after this. Oh yeah, a failure case. So Berkeley did a fantastic job. Berkeley did such a good job. I went out and spent some time at Berkeley with the team and got to learn more from them about what they were doing, and it was a fantastic time. Mostly because before that, I was a part of this, and we completely failed to do it. I failed to do it. The fantastic graphics, the game, everything was by Hayden Scott Barron and Dave Sweeney. Did a fantastic job on this, and then I butchered the AI, and I wanted to share that with you today. Okay, so it's a very simple game that we did in the game jam. I can't remember what we called it. The video will say soon, hide and seek. It was a really inventive name that didn't stick with me. So the mouse is going to run around some of these mazes. We've got like procedurally generated mazes. The mouse has to collect the cheese, but it needs to stay away from the bird, and the bird's going to like capture it in various ways. That I don't know how many of them are in the video, but what the mouse can do is it can hide. Right? The bird can only see from above. It can't see where the mouse will hide. So this is some nice idealized footage of actual humans playing the game. And this is what the AI did. It's going to play. So the mouse runs to that bush. And it likes that bush. It really likes that bush. So I started this off with like just trying to learn both of them at the same time. I completely ignored all of the advice that I gave earlier. Right? I just set two agents off learning. Didn't learn anything, right? Like the full stack was there, multi-agent learning, couldn't get anywhere. So I scripted the behavior of the bird and then just learned the best response for the mouse, which was, go to that bush. Everywhere that this mouse starts, it goes to that bush because all it's doing is maximizing reward against that one fixed policy, right? As soon as you put a human in here, the human's going to defeat this mouse very quickly, right? Because this mouse has never seen any other policies. It just sees that. Okay, it's a ridiculous example where it goes to the bush. Like it always goes to the bush. It was really frustrating at the time that this went to the bush so many times. Like at points, it starts further away from the bush like this. We're like, maybe it's not going to the bush. Maybe it's learned something else. But it goes to the bush. But yeah, a ridiculous example to try and make the point. You need, if you're going to train an agent that's going to act with other humans, and humans are going to act in different ways, you need to maintain a population or a set of different policies to learn a best response to. Okay, it can't be the self-play thing is great if you just want to, like, it's good for adversarial games. Fully adversarial, you just want to learn how to defeat something. Fine, that's fine. The worst you're doing is like leaving cash on the table if you do that. But for collaboration, you really need to model what the other humans are doing in the environment, how they're acting, and learn how to respond to that. And this isn't like a one-off thing. And again, this is why I really like this far cat end of the spectrum. It's not, whilst we tend to ship fixed policies, learned policies, this becomes an iterative updating, right? Like you'll see how players interact with the agent, and players will find a way. I don't think I need to tell this room, players will find a way to mess with your agents and do things, but then we've got that data. And if that's a behavior that we want to get rid of, we can model that behavior and we can learn how to respond to it. Okay, so it's an iterative process of maintaining this set or population of other policies and learning how to respond to them. So that's mostly what I had today. Key takeaways. It's unwieldy and it takes a lot of time. In roughly 2019, 2020, we went out and we surveyed a whole bunch of people from different studios about their uses of machine learning in things. And this quote, which we used as the title of the paper, which goes into like how people were responding to using it at the time, really stuck with me. Like, it is hard, right? It's not trivial, but if you reduce things down to supervised learning, I think you'll have a much better time than just believing the hype and letting things run, okay? In particular, my recommendations are just learn one reward maximizing algorithm really well. There's so many reinforcement learning algorithms out now, and they're all just little tweaks of hyperparameters and things, so people could get their next NeurIPS accept and go to the parties, okay? You don't need that. PPO in particular, or whatever PPO has evolved to be in the open source community by this stage, and if anyone wants to talk about evolution of algorithms in the open space versus closed space, I'm more than happy to go into that over the coffee break. But PPO, some really good implementations of them are here now in Unreal. I very much recommend just one, learn it really well, and personally I recommend PPO. Then to imitate and get like a good human-like character, I recommend blending PPO with behavior cloning. And this will get you a more human-like agent. And to collaborate, maintain this population of agents. That's everything I had. Here's a bunch of things that like super helped me to progress on this, like really nice practical, not particularly the papers and stuff, but really practical implementations of how to get it to work. And there's loads more in the bonus material of the slides, which I believe we're going to share with people afterwards. Thank you.